Okay, so now we're going to start with buckling, part 2. Part 1 was more theoretical, kind of understanding the concept of instability. Part 2 is looking specifically at structural members that are experiencing bending as a result of the instability with their compressive load. So we're going to go through and we're going to derive the equation of the critical buckling load for axially loaded members. Okay, so if we start with a column, and we'll put our x direction vertical, and before we get started too far, no, it's okay. So our y is going to be to the right. Now we need an axial load applied, so P comes down from the top. When this becomes unstable and deflects, it's going to deflect like that. So it has the pin and the roller that stop it from deflecting at those points. The roller at the top will come down a little bit, and then the member will bow out sideways. So if we look at a small segment, so that segment comes from here. It has some internal forces at the top and bottom of the segment. So we have say vertical forces. We'll call that Rx and Rx plus delta x. Vx and Vx plus delta x. And then moments, there's internal moments as well. So this would be M at x and M at x plus delta x. We can look at equilibrium to get some information about this member. So we can say that the sum of the forces in the x direction equals 0. Now, mind you, x is vertical in this situation. So that says that R of x minus R of x plus delta x has to equal 0. And if delta x is very small, this becomes dr dx, right? This is essentially just the change in R. And we say, so that must be equal to 0, which this implies that R is constant. And what's going to be the value of R? It's constant and equal to P, the load. Exactly. So that's not surprising, but we've mathematically shown that that has to be the case. Okay, so the next thing we can do is we can look at the sum of the forces in the y direction. And we'll say that the sum of the forces in the y direction must be 0. So that's now the horizontal direction. So we have V at x minus V at x plus delta x equal to 0. Once again, if we make delta x small, take the limit as it approaches 0, what we're going to get is that negative dv dx equals 0. So this tells us once again that V is constant. Now for a moment, I'm just going to leave it at that. We're not going to talk about what V is equal to, but we will come back to that shortly. First, before we go there, I want to look at the sum of the moments. So the sum of the moment is equal to 0. And let's take our summation about the bottom of this element. So we can say that m of x plus delta x minus m of x. Now we have moment coming from the shear force up top. So we'll say minus v of x times delta x. And we also have shear force, or sorry, moment coming from this vertical load because it's offset. Because of that deflection, it's now offset from the point we're taking the moment about. So that's a positive moment. That's r of x. Now we need to make a decision at this point how we're going to notate that deflection. Would you like to use would you like to use v or y? Is it okay if we use y? It's the same as the v that we've talked about before, but here y might be simpler. Okay, so that distance, that offset, is the difference between y at x plus delta x and y at x. So both of these points are deflecting some, right? We have this deflection and we have that deflection, and it's the difference between those two deflections that create our moment arm for that axial load. And this all must equal 0. We can divide this by delta x, and then we can make delta x approach 0, and what we get is dm dx minus v plus r times dy dx equals 0. Does this portion of that equation look familiar? Where did we see that? Maybe dm dx equals v? Shear and moment diagrams. The slope of your moment diagram was equal to your shear. Right? It's the same, this is the same concept, right? That was dealing with bending of the member. We have bending of the member here. The difference is that now we also have this term with an axial load that's offset. Before we didn't have any axial load, we just had bending. Now we have axial load applied. So that this last term is a new term that accounts for the axial load. We've previously agreed that R equals P, correct? So we can substitute P in place of R. And now let's go back to V. V is a constant, V being the horizontal force. If we go back and look at our initial system and we have a load P, we have, oops, I think I mixed those up. We have the roller at the top, the pin at the bottom. So the reactions would look like this. Then there might be some reactions here. What are these horizontal reactions? There's 0. If all we have is this applied vertical force, there's nothing causing horizontal reactions, therefore those are 0. So if one of those is 0, say the top one is 0, and we take a section cut, what does this shear force equal? 0. If it equals 0 anywhere, it has to equal 0 everywhere, right? Because V is constant. So what that means is we can actually cross this term out of our equation.
Sure. In the image you have, there's a force in the, I think that's the y direction, because the beam is bending. Right?
There's only an applied force in the vertical direction.
Yeah, well, because of the fact that it's focal, doesn't that mean there's no force in the direction?
No, not necessarily. All right, so let's clean this up a little bit. We have the equation dm dx plus p dy dx equals 0. All right, so we can integrate with respect to x, and this becomes m plus py equals 0. Nope, it doesn't equal 0. Sorry, what does it equal? What happens when I integrate? C. It equals some constant c. Now, up until this point, everything has been generic. I gave you boundary conditions of the roller and the pin, but they haven't affected our solution. No matter what types of reactions they were, they would not have had horizontal forces. And so we still would get the 0 shear. Nothing would be different if you changed those boundary conditions. So up until this point, this is a generic solution. But we're about to customize it for our boundary conditions. So in particular, we know that the moment at 0 is equal to 0 because we have that pin. And we know that the deflection is equal to 0. So if I plug in 0 for my moment and 0 for y, what must C equal?
0.
0. So therefore, C equals 0. And so we end up with the equation m plus py equals 0. Now, we can relate our moment to our deflection. Does anyone remember when we were doing beams and we talked about beam deflection? Does anyone remember that equation? M equals, it's a function of y. Had some material constants in it. Yeah, it has EI. And in the past, I believe we used the letter V, but we can replace that with Y. Is that it, or am I missing something? No, it's not divided by something. Yeah, perfect. The moment is EIY double prime. So Y is your deflection. The first derivative of Y is your slope, right? dy dx. The second derivative is the change in your slope, the rate of change of your slope, which is also referred to as your curvature. So we've got m equals EI y double prime. So our moment is related to our curvature. The more moment you apply, the more this beam curves. Excellent. So I can plug that in. And what does that look like? Said it looks like a differential equation. And let me help you out. Let me make it a little more clear. There we go. You recognize that as an ODE, ordinary differential equation? Okay. So in Math 81 or Engineering 101, you should have learned how to solve these. Anyone remember the solution? Y equals? It has a cosine in it. Yep. This feels a little bit like Wheel of Fortune. Does it have a cosine? Yes, right here. Anything else? Maybe a sine? Is there a sine? Maybe some constants. We'll say A and B.
A plus bx.
Yeah.
Or in this case, with x equals to x.
Okay.
Plus b sine bx plus x.
Is that what you're saying? Is that? And actually, we need square roots. Yeah, it's the square root of whatever the coefficient of y is, goes in that sine and cosine term. Okay, so Math 81, direct application. We have a relationship that came from equilibrium that turns out to be a differential equation. And the solution to that differential equation will tell us the shape of our deflected member. And it's of the form constant times cosine square root p over ei times x plus b sine square root p over ei times x. Okay, so now we need to figure out what these constants are, which we can do using our boundary conditions. The boundary conditions we have are that at y equals 0, or sorry, at x equals 0, y equals 0. We have no deflection at the top. We also have no deflection at the bottom where x equals L. So let's plug that in. We can say y of 0 equals 0 tells us 0 equals a cosine of 0 plus b sine of 0. What is the sine of 0? 0. So this term is nullified. So this first term, though, cosine of 0 is 1. Therefore, a equals 0. So that means this term, this first term in our deflection equation is not, it's part of the general solution to an ODE, but it's not a part of this specific solution. So now we can take a look at the other boundary condition and see if that gets us meaningful information. So we have y of L equals 0. That tells us that 0 equals b times the sine of p over ei times L. So what are the two ways that we can make this equation satisfied? Yeah, so either b is 0 or this term is 0. Now, b equals 0 is a really sad solution because b equals 0, you beg to differ? But it works. It does work. But it's sad and disappointing in the sense that we don't get any deflection. And so remember I told you last time that buckling doesn't necessarily mean that it deflects. It means that it's unstable, and with a disturbance, it will have a large amount of deflection. So this right here mathematically shows you can satisfy this situation with no deflection. But that's not what we want. We want the deflection to happen so that we can calculate at what load it would happen.
What would it look like?
It would look just like a normal column, just sitting there. You wouldn't know it. Yes, yes. Now, I mean, it's extremely difficult for this to actually happen because everything has to be perfectly aligned, but that's part of what makes it so dangerous, is that it looks fine. You can't tell that it's reached that load. The only way you tell is you see it deform laterally. All right, so we need to make this other term equal 0. How do we make that other term equal 0? P could be 0. But that's another like sorely disappointing. L is 0. Okay, so we can have no length or no load, but none of these are really like satisfying situations. So how about how about P over EI square root L equals pi, or some integer of pi? Would that work? Unfortunately. Okay. So we can pick any number for our integer. We can pick 0, but then we're back in the same boat. Everything is always equal to 0. Okay, but we can pick any other number, say 1, 2, 3, 4, 5. But I would suggest we pick 1, because 1 is the first number you're going to get to. So as you're exciting the system, it's going to deflect in a manner that is commensurate with that first mode. You have to excite something with more energy to get it to go to a higher mode. And so higher mode might mean that instead of deflecting like this, you're now deflecting like that. So let's just say that n equals 1. L, E, and I are defined by the problem. If we have a specific member, we already know what those are. Pi is always known. So the only thing unknown in this is P. So we can solve for P, and we say that P becomes pi squared over L squared times EI. And this now is what we refer to as our critical buckling load, and it's an extremely important equation, so it gets the red box. So your critical buckling load for this pin-pin situation is pi squared EI over L squared. Now, we never actually solve for B, and we don't really care.
That's only for pin-pin situation.
This is specifically for pin-pin. At the point that we started using our boundary conditions to determine things, we started customizing it to a pin-pin situation. No, could be anything. So, but you don't have to derive the others. You can go through the same derivation, and on Saturday night, I know you have nothing better to do, so you could do this Saturday night. You could derive for all the different conditions. But I'll give you the answer right now so that you know what you're expecting to get, okay? So if you went through this derivation for the other loads, so some of the other, or not loads, but other configurations, yeah, some of the other ones are, say, pin fixed or fixed fixed. But now when I say fixed fixed, you got to use your imagination a little bit. It's more like something that looks like that, where it can move vertically, it just can't rotate or move laterally. You have to be able to move vertically for this to deform. Otherwise, if you don't move vertically. What's that? Okay, duly noted. And then the last one to consider is like a flagpole, where it's fixed on the bottom and free on the top. All right, so if you look at the equations for this top one, P critical is pi squared EI over 0.7 L quantity squared. The second one is P critical equals pi squared EI over 0.5 L squared. And this bottom one is EI over 2L squared. Do you notice anything? Pi squared EI is common to all of them.
Over a length squared.
Over some length squared. And that length seems to be changing depending on our boundary conditions. So a more general form is pi squared EI over effective length squared. And what I mean by effective length is that if you look at the shape this takes when it buckles, that's directly related to the load it can withstand. So in this top example, you find the inflection point somewhere about here. Remember, the inflection point is where it goes from being concave one direction to concave the other. So this distance from the pin, which is also an inflection point, you have zero moment there, so that makes it an inflection point. This is 0.7 L. Down here, the distance between these two inflection points is 0.5 L. Now down on this last example, you have zero moment at the end, and you have maximum moment at the bottom. So you never get to a second point of zero moment, but you can imagine that this continues down symmetrically. And so at a distance of 2L, you would eventually get back to a point that would have zero moment. You're only really seeing half of the curve length in the member itself. So the takeaway is that the more constraint you have, the higher your critical load.
So,
Yeah, it's the length that the deflected shape, it's the length along the deflected shape from points of zero moment. And I said along, but that's not really that great. It's the vertical length between points of zero moment.
Sorry. Doesn't mean in these diagrams, if you section the center of like the beam, you won't find any shear stress.
Correct.
There will be no shear stress.
Let me see.
Because it looks like there should be.
According to the theory, there shouldn't be. But remember, what is this class all about? A series of simplifying assumptions. So according to the theory, there is not shear stress. And actually, let's be very careful with that. Maybe it's not that there's not shear stress, there's not horizontal reaction. So the more curved that member becomes, the more, so in this region here, if this member becomes curved, what I'm saying is there's no horizontal force, but that vertical force might start becoming more and more shear as opposed to axial. And we teach you these things like they're facts and laws and indisputable. But at the conference that I was just at, they gave a very interesting talk on the history of the design of columns, and this hasn't always been widely accepted. When Euler came up with this, it was largely disregarded for a long period of time. And the reason for that is that it only applies when the members start to become more slender. So for example, if you have, well, let me first show you the slenderness ratio. And then I'll explain what I was about to say. So if we want to express this in terms of stress instead of load, we need to divide the critical load by the area. But recall that area is equal to the moment of inertia over the radius of gyration squared. So that means it becomes pi squared EI over I over R squared LE squared. So you can express that as pi squared E divided by the ratio LE over R squared. So it's the radius of gyration, not some radius measurement. This LE over R is what we call the slenderness ratio. So that's the slenderness ratio.
That's length divided by radius.
It's effective length divided by radius of gyration, which is I times A. Square root of I times A. No, sorry. Square root of I over A. So if you plot that slenderness ratio versus stress, Euler tells you that this is your capacity, and as you get shorter, you get significantly more stress capacity. But there's a region in which you're actually governed by your yield stress. There's a region in which, even though Euler says you get this much capacity, you're never going to experience that because your member will yield or fail due to a lack of strength before it becomes unstable.
What were you saying just now?
What I'm saying is that we can calculate the critical buckling load or the critical buckling stress, and that'll give us the red line. But that's only meaningful if instability is going to happen before compressive yielding. If instead your material is going to yield and fail in compression, then that needs to be your design value. And so my point was, the farther back you go, the more stout the members were that they were using. They were using giant blocks of marble or some type of stone, and they would say, that your formula makes no sense. Look, this thing has failed. And anyway, because they were operating in this region. All right, so we have an in-class assignment for you. And what I want you to look at is a W section that has fixed, and conditions. So this W section, cross section looks like that, more or less. So these lines that you're seeing here are those flange outlines. This member has properties of, area equals 14.7 inches squared, moment of inertia, I is equal to 56.3 inches to the fourth, and the yield stress, sigma Y, is equal to 50 KSI. And I told you it's fixed. What I want you to calculate is the critical buckling load, P critical. And then I want you to calculate the factor of safety against buckling if we apply a load P equal to 150 kips. And then once you've done that, I want you to check whether that P critical is less than or equal to sigma Y. So, or I guess not P critical, but is the critical buckling stress in this region here where you're greater than sigma y, or is it in this region here where you're less than sigma y? So that's your third thing to check is sigma critical less than sigma y. Okay, let me know if you have any questions. Okay, so you should, if you've worked on this problem and gotten this far, you should be getting approximately 1120 kips for your critical buckling load. To get your factor of safety, you take that 1120 and you divide by the 150 that's being applied, and that gives you about 7.6, so it's a pretty good factor of safety. But you have to check against yielding. So you compare this, see 1120 kips divided by the area of 14.7, and that gives you about 76 KSI. Your yielding occurs at 50 KSI. So really 50 KSI is the maximum you're going to be able to load in this column. So if you really want to know a factor of safety against against buckling, you're going to need to take this 50 KSI, figure out what load that applies to, and then redo this calculation here using that applied load instead of the 150. All right. Okay, so with the last few minutes, I want to show you one more concept or example. When it comes to buckling, oftentimes the problems are going to be heaviest on the static side. The buckling is one equation that I've just given you, pi squared EI over effective length squared. So it's one equation that as you can see, you can spend 2 minutes calculating it. So in order to make the question meaningful, oftentimes it's the statics that creates the most difficulty. So just to show you an illustration of what I'm talking about, we might have this contraption here. Where we have 4 different rods that are all attached with pin connections. So these are different links connected, and say this is a handle that we apply a force to, so it's a lever. And we have different dimensions, so this might be 12 inches, 4 inches, 2 inches, and 15 and 20. So the question might be, how much load P can I apply before these members buckle? And assuming that this end here jams in and acts as a pin. So now you have 2 pin-pin members, and you want to know at what point do they buckle or do they become unstable? And so to calculate that, first you need to do the statics. So you have this member over here that's acted on by P. You know there's some reaction. You can take the moment about this base, so you never have to solve for that base reaction, but you do have to take the moment about it to get these results. So the sum of the moment has to equal 0, which means that if you take this reaction, R1 times 4 inches, so we'll call this R1, minus P times 16 inches, that tells you that R1 has to be 4 times P. So you're amplifying your force 4 times when it goes into that member. And then if you want to calculate the critical buckling load, you'd say, okay, if I'm applying 4P, I know that the critical buckling load is pi squared EI over length squared. In this case, the length is going to be 15 because it's pin-pin. And then you plug in E and I. Then you back solve for P. So that gives you some value of P critical. And assuming these are steel members with 1 inch diameter. So steel with 1 inch diameter. And it's a special kind of steel. It's L2 steel, which means that it has a yield stress equal to 102 KSI. All right, so if you plug that in, what you find is that P equals 15.6 kips. I can apply 15.6 kips, at which point this member becomes unstable. And I can do the same thing for the other member. Now I need to look at its free body diagram. I know that there's this force coming in here that's equal to 4P. And then I have a reaction at the top. And if I take the sum of my moments equal to 0, I can say that R2 times 6 inches minus 4P times 4 inches has to equal 0. So that means R2 16 over 6, 2.67P. Perfect. So we can then set that up equal to pi squared EI over 20 inches squared. And then you solve and you get that P equals 13.2 kips. So now what you see is that at 13.2 kips, this member on the right would buckle. So that's actually the governing member of this system. That one becomes unstable first. And then if you wanted, you could take a look at whether these things are going to yield or buckle. So you could compare these loads. You divide this by the area, and then you compare that to the 102. Same thing here. You would divide by the area and compare that to 102 KSI. If it turns out that either of those is larger than 102 KSI, then it's that 102 KSI and the force that produces that stress that would govern your design, because you wouldn't want to use this past yielding. Questions? No? Okay, then that completes it. You've learned everything you need to know about mechanics and materials.